Hello and welcome. We will continue with factoring polynomials, but this time we're looking at polynomial expressions where the leading coefficient is different than 1. With leading coefficient being different than 1, the rules or the process of factoring will change slightly, and we'll point out at those changes and discuss them together. As our first example, I've taken an example of a trinomial of second degree. And that's because we already know how to factor this without the need to use the remainder or the factor theorem. I'm going to use a method that is called breaking down the middle term. That's the one that you have been taught most probably in grade 10. And the middle term in this polynomial is 17x. So 17x must be broken down into two terms that again add to 17 because we cannot change the value of the expression, but the product of the two numbers that add to 17 must be equal to the product of leading coefficient with constant term, which is 30. So the two numbers that multiply to 30 and add to 17 in the meantime are 15 and 2, because 15 times 2 equals 30 and 15 plus 2 equals 17. So we're going to break down the middle term into 15x and 2x. So our polynomial here will change to become 6x squared plus 15x plus 2x plus 5. So the value of the polynomial has not changed. It's just the way it looks that has changed, which means the middle term, which is broken down. Now the next thing that we want to do is group the first two terms together and the last two terms together and take out the greatest common factor from the first two terms. In our case is 3x, and in brackets we're left with 2x plus 5. In the next group of terms, we don't have a common factor. When that's the case, we write 1, 2x plus 5. And now the factored form must be, we have a common binomial of 2x plus 5. And the other factor will be 3x plus 1. So we are going to say that 2x plus 5 and 3x plus 1 are factors of 6x squared plus 17x plus 5. Now when you think about it, 2x plus 5 is a factor of this expression, which means that at x equals negative 5 over 2, this expression must be 0. Which means that, and that's what makes 2x plus 5 a factor, right? The fact that the remainder will be 0, or the value of the expression at negative 5 over 2 is 0. So when we are factoring polynomials by using the factor theorem, these are the numbers that we search for. So we need to know the coefficients 2 and 5. So the question becomes, when you use the factor theorem, how do you figure out these numbers? Now remember that when we factor polynomial expressions where leading coefficient was 1, we only looked at the last term, the constant term, and we searched for the values of b based on the value of the last term. So we said that the possible values of b are the factors of the constant term. When you factor polynomials where a is different than 1, this doesn't change. So the values of b will still be the factors of the constant term, so plus, minus 1, plus or minus 5. When it comes to the denominator, so this number in here, you can tell that this will depend on the values of the leading coefficient, because the number 2 is the coefficient of x, and Also, this denominator here, number 3, right, is the coefficient of x. And these two terms multiplied together are the ones that will give us the first term in the polynomial expression. So their coefficients will produce the leading coefficient, which is different than 1. And it only makes sense to say that the values of these numbers, so 2 and 3, must be factors of the leading coefficient. So we are going to say, in other words, that if this is something in the form b over a, then b must be a factor of the constant term, whereas a must be a factor of the leading coefficient. So we're going to say that the values of a are possible factors of 6 in this case, so plus minus 1, plus minus 2, plus minus 3, and then or plus minus 6. Obviously, it cannot be all of them, so it's only 2 factors in this expression. So this is how we investigate or search for the values of b over a in factoring polynomials where coefficient a or leading coefficient is different than 1. So I wrote down the steps here for you to have them. Remember that the rational zero theorem states that the factor, or ax minus b, sorry about that, is a factor if the value of the polynomial at b over a would equal 0. And if x at b over a is a rational zero of the polynomial, then b will be the factor of the constant term, and a will be the factor of the leading coefficient of the polynomial. So b will depend on the value of the constant term, and a the leading coefficient. So therefore, to search for the factors of polynomial when the leading coefficient is different than 1, we must follow the following steps. First, we must list all the possible factors of the constant term. This will give us the values of b. And then list all the possible factors of values of a, of the leading coefficient that would give us the values of a. And then we have to create all the possible combinations of b over a. And last, we have to investigate which value, so which b over a, would make the polynomial 0. And once we find that value, then we are going to say that ax minus b, depending on what values we get there, right, would be a factor of the polynomial. Let's get started with an example. So we have 8x cubed minus 4x squared minus 2x plus 1. I'm going to start with possible values of b. And we're going to say that the values of b will depend on the constant term in the polynomial. So that means we have simply plus or minus 1. The next thing we want to do is find the possible values of a. And the possible values of a are derived by, or are derived from the coefficient of the first term. So the value of a is, or possible values of a, plus minus 1, plus minus 2, plus minus 4, and then plus minus 8. So the combinations of, the possible values of b over a are And here we have a lot of work to do, as a matter of fact. But remember that once you find the first factor, it's very easy afterwards, because you divide and you get a quadratic, which you can factor without the need or without having to use the factor theorem. So the way we do this is this. We take first the one of the values of b, plus 1. And then we say we want to combine it with each and every value of a. So 1 over 1, 1 over negative 1. Okay, sorry. I'm going to do it, call it 1 over positive 1. And then 1 over negative 1. And then 1 over 2. And then, sorry, here. And then we have 1 over negative 2. And then 1 over 4. And then 1 over negative 4. And then 1 over 8. And last, 1 over negative 8. Now we have to work with a possibility of b being negative 1. So what happens in this case is this. So we have negative 1 divided by 1. Now remember, negative 1 divided by 1 is the same as this term here, which means that we don't have to write it twice. So what we are going to do is ignore this. The next one is negative 1 divided by negative 1. So we kind of get the same thing in here. So plus minus 1. So what is happening in here actually is a very similar alternation of the signs. So which means that we should stop at this point and think that, okay, so these are, and be happy with the values of b over a that we have actually listed in here. Now, the next thing that you want to do is find out or test each and every value. So I'm going to start by testing the first number. I'm going to go blue. So the value of the function at 1. That's the 1 over 1 here, okay? So we'll say that is 1 to the power of 3 times 8. Minus 4, 1 squared minus 2 times 1 plus 1. That will be a number different than 0, because we have 8 plus 1, 9, minus 6, 3. So we're going to say x minus 1 is not a factor. Won't work. Here, I don't like to write a lot of x's. So the other one is f of negative 1. So 8 times negative 1 cubed minus 4 times negative 1 squared minus 2 times negative 1 plus 1. So that's negative 8. And then negative 4 times positive 1, negative 12. And then plus 2 is 10. Plus 1, 11. So we're going to say different than 0. Therefore, x minus negative 1, which is x plus 1, won't work. We'll keep on searching. Remember, you can do these searches in your calculator, so you don't have to show all this work. F of 1 over 2 this time. So we have 8 times half cubed minus 4 times half squared minus 2 times half plus 1. So this will be 1, this will be minus 1, this would be minus 1 as well, and this is plus 1. Oh, it seems that this time we hit a 0. And we're going to say that, therefore, x minus 1 over 2 is a factor. But we don't want to write the factor with fractions ever. So we're going to say that 2x minus 1 is a factor. And once we found the first factor, we're going to go ahead and divide the polynomial by 2x minus 1. We're going to use synthetic division. And we have 8 as our first term, negative 4, negative 2, and positive 1. Here goes our little rectangle, half rectangle. And we're going to have positive 1 over 2 here. Bring 8 down, times half. That's a 4. We get 0. Multiply by half. Negative 2, we multiply by half, negative 1, and then 0. So remainder is 0 as promised. Now remember that we are dividing by a binomial where a is different than 1. So that means we have to divide by this number here, each and every coefficient. So 8 over 2, 0 over 2, negative 2 over 2. And stick the variables to each and every term. So here we have x squared, here we have x, and here we have nothing. So we're going to say that so far we have brought the polynomial in the form 2x minus 1, and then multiplied by 4x squared. That's because 8 over 2 is 4. And then plus 0x, you don't have to write that, minus 1. And now you can factor a little bit more. So we're going to say f of x equals 2x minus 1. And 4x squared minus 1 is the difference of squares. So we go 2x squared minus 1 times 2x squared plus 1. And with this, 2x minus 1 and 2x plus 1. Okay, so this would be the factored form of the polynomial expression, and that's our answer here. Now we have another example that I would suggest that you attempt on your own. It's 4x4 plus 6x cubed minus 6x squared minus 4x. So I would prefer you try this on your own, but I will go over the example. As you see in here, you have a common factor you can take out, and that can be the case sometimes. So we'll take out the common factor, which is 2x. Then in brackets, we have 2x to the power of 3 plus 3x squared minus 3x minus 2. So we already have one factor taken out, but then we have to take care of this polynomial of third degree. So we're going to focus only on this part. We have a polynomial where the leading coefficient is different than 1. So we're going to say that for the possible values of a, maybe we should start with b. We have to refer to the constant term. So we'll say plus minus 1, plus minus 2. And the possible values of a are also plus minus 1 and plus minus 2. Therefore, we'll say the values of b over a will be plus minus 1 over plus minus 1, plus minus 1 over plus minus 2, plus minus 1, plus minus 2 better, over plus minus 1, and plus minus 2 over plus minus 2. But notice how plus minus 2 over plus minus 2 is technically the same as plus minus 1 over plus minus 1. So when we list the possible values of b over a, we're going to say that's plus minus 1, plus minus half, and plus minus 2. We're going to test each and every possible b over a in the expression. So I'm going to start with plus 1. So 2, 1 cubed, plus 3, 1 squared, minus 3 times 1 minus 2. So that will be 2 plus 3 minus 2, which is 0. So we've hit the jackpot with the first attempt. We're going to say that x minus 1 is a factor. And now that we know that x minus 1 is a factor, we'll take the coefficients of 2x squared plus 3x minus 2. And we will divide by x minus 1. So we have 2, 3, negative 3, negative 2. Here goes our half rectangle. And here goes number 1. Bring 2 down to 5, 2, 2, 0 here. So here we go, x squared plus 5x plus 2. So far we have arrived at y equals 2x times x minus 1 times 2x squared plus 5x plus 2, or 2x, x minus 1. And now we have to figure out the other two factors. So we have 2x and x. We don't need the factor theorem for that. And here we'll go plus 2 and then plus 1. That will make a sum of 5. And with this, we have factored the given polynomial. And we're done. So here's an example of a thinking question. And in this example, we are given a polynomial, but not all coefficients are known. And what we want to do is find the coefficients given that we know the remainder when the polynomial is divided by the given binomial, so by x plus 1 and by x minus 2. So this is sort of a thinking question. You most likely will see questions like this in your evaluations. So I'm going to write a note in here. So we have a polynomial 2x cubed minus mx squared plus nx minus 2. And we are told that when divided by x plus 1, the remainder would be negative 12. And when divided by x minus 2, well, it says that x minus 2 is a factor, then the remainder must be 0. Now, knowing that the remainder is equal to the value of the polynomial at b, we're going to say that the value of this function at negative 1 would be negative 12. And that same function at 2 will have a value of 0. So I'm going to call this px, so it's easier for us to communicate the solution. So p of negative 1 must equal 2 times negative 1 cubed minus m negative 1 squared plus n times negative 1 minus 2. Now p of negative 1 is negative 12. That's negative 2 minus m minus n minus 2. As you see, we ended up with two variables. We already had them, so take negative m and negative n in to the other side, m plus n, and then bring negative 12 to the right side as a positive, and then we have minus 4. So the first relationship that we discover here about m and n is that, hey, m and n is 8. So what I'm going to do is I'm going to circle this equation because I am going to need it later. I can't use it right away. I need a second equation to figure out what m and n is. Remember, when an equation has two variables, you need two equations. If it has three variables, you need three equations to solve, and so on. So the next one is p of 2 equals 0, which means p at 2 is 2 times 2 to the power of 3 minus m times 2 squared plus n times 2 and then minus 2. So 0 equals 16 minus 4m plus 2n minus 2. Take 4m to the other side and the n term as well. So 4m minus 2n equals 14. Now, we're almost done, but usually what I like to do is check and see if I can reduce the coefficients, because the smaller the better. And then we go 2m minus n equals 7. This will be our second equation. So what we're going to do is use both equations to find m and n. And in order to do this, we are going to bring them together to a system of equations. This is how I like to write a system of equations. First of all, I like to keep my terms in order, so if the variables are in the left side in the first, then they must go on the left side in the other as well, and the constants in the right side. And I also like to use these braces that shows me that these two equations are connected to each other. Now, obviously, you can use any method of your choice, substitution, elimination, but I would go for for elimination this time. Elimination is an easier way to solve systems, and in this case, I can solve very easily because n and negative n are opposite in sign, and I can easily eliminate n by adding the two equations. So we have m plus 2m 3m plus 0n equals 15. So if 3m equals 15, makes m equal to 5. Well, if m equals 5, then knowing that m plus n is 8, that makes n equal to 8 minus m, or 8 minus 5, so 3. So we're going to say, therefore, the coefficients are m equals 5 and n equals 3. It is very important to distinguish them, or to write them separately, because sometimes I notice people do this. Remember, they're not an ordered pair, okay? So please don't make this mistake. It's a big mistake. So this is all about factoring polynomials, and I hope everything so far made sense. And I would encourage you to practice a lot of them, as much as you can. I will see you